there are two vector field integration you can do. However, for the surface integral, we only have this one type of integration with respect to a given vector field. There's no tangent direction anymore. Because the tangent direction can be given by RU or RV prime and by any linear combination of these two. All right? If you have a surface, we cannot really talking about a tangent vector anymore. That with me? So talking about integration, we have to have a tangent plane, but we don't have one particular tangent vector you can always fix. Okay? So for a surface integral of a vector field, we only have this one thing, okay, which is essentially the flux. Okay. So the flux of the vector field on a surface is the inner product between the vector field and the normal, and the formula says this guy is equal to a double integral of f dot product with the normal. Okay. So I can reduce the surface integral of a vector field on a surface to a double integral on u and v. And integrating function is the inner product between the vector field and the normal. Okay? So here is one extra step we have to take care of, which is about the normal vector direction here. Because the normal direction can be given by the cross product between RU prime and RV prime, or the opposite direction. Now with me? So if I have the normal direction fixed, then I have to choose the proper sign right here. All right? I have to choose the proper sign here. So that is a plus or minus sign I have to decide right here, which is given by the orientation of the normal vector. Okay? So there is one extra step I have to take care of, which is if I'm taking the surface integral of vector field, then I need to do the dot product between the vector and the normal. But now I have to worry about which normal it is. Okay? In terms of whether I want to have a plus RU prime times RV prime or minus. So which direction I have to fix. That's one step. But this step is usually a very easy step. You don't have to worry about too much. And I want you to compare these two surface integrals. So surface integral of a vector field, I do have to care about the orientation in terms of plus or minus here. But surface integral of a scalar function, I don't have to care about that, right? Because you have length of the normal. You don't have to care about the direction anymore, okay? So I will give you a couple of examples about why and where this orientation is coming. So let's look at the formal integral. So f, in this case, is a very easy vector field, 0, 0, minus 3. So this vector field is just a constant vector field, right? So x, y, z as functions are all constant functions. Whereas my surface here is given by the equation z is equal to 6 minus x minus y, restricted in the first octet. So we want to compute the surface integral of f n ds. Okay, that's what I want to compute. Again, what's your first step? What is your very first step? Parametric equations. So if it is a line integral, get the parametric equation of the line. If it is a surface integral, you have to get the parametric equation for the surface. So I want to have R, U, and V, where I want to assign rows for U and V correspondingly. And then I want to figure out what X is, what Y is, and what Z is. And the easiest choice, and the easiest to try you should always begin from is to set up X equals U and Y equals V. And it will work for a lot of different surfaces. It works for the paraboloid, and it is going to work for this, what is this guy?
Plane.
This is simply a piece of plane, right? If you want to draw it, this is going to plane restricted to the first object, and this is where it is. So 6 here, 6 here, and 6 here. So this is a plane restricted to the first term. You can still go for the xy trace, yz trace, and xz trace. And also you can find these x-intercept, y-intercept, and z-intercept easily. Okay? Okay, so x is equal to u, y is equal to v, and z is simply 6 minus u minus v. Right? And then I want to compute the tangent vectors. Right. So tangent vectors for our u prime. 1, 0, 5. And minus 1, am I right? So tangent vectors are all about taking derivatives, right? So RV is equal to, what is RV prime?
Maybe 0,
0, 1,
-1.
minus 1, okay? And then I want to get the RU prime times RV prime. And in this case, our orientation of the surface is that the normal points upward. Okay, so if we set up what our normals are, and the normal directions are pointing upwards, which means, how do we translate this sentence? The normal point upward. Z component is positive. Okay, so upward is actually telling us Z component is positive. Downward means Z component is negative. Okay, and then we need to compute what the cross product is. Again, this cross product between the two tangent vectors might give you the actual normal vector, might also give you the opposite of the normal vector, depending on whether your Z component of the cross product is positive or negative. Right? If it is positive, this is exactly going to be the normal vector we fixed in the very beginning. If it is negative, we need to flip everything, right? To get the negative of the cross product. So our U plus our prime, still, if you're working really smoothly without the imaginary RDK here, you can just work out the 3x3 matrix computation directly. So the I component is going to be 0, minus 1, I got a 1 here. So the J component is 0, minus 1, I got a 1 here. And the K component is just 1. So the Z component is positive. Therefore, the normal vector is exactly equal to 1, 1, and 1. Right? Now, I have to be a little careful here. Because when we have the restriction, when we have the parametric form of the equation, I haven't really write down the restriction of UV yet. What is our restriction for U and V?
First octet.
It is in the first octet, which means X has to be positive, Y has to be also positive, but Z has to be also positive too, which means I have to make 6 minus X minus Y to be greater than or equal to 0. So X is greater than or equal to 0. But in this case, it's simply U greater than or equal to 0, V is greater than or equal to 0, and 6 minus U minus V is greater than or equal to 0. In other words, the restriction is simply the region right here. Right? What is the type of this region? If I want to do a double integral with respect to this region, it's a U simple, it is also a V simple, right? So this is both U simple and Y simple. I'm refreshing your memory about double integral and triple integral constantly. Okay? So now I want to do S, F dot, and ds. This is simply equal to the double integral with respect to U and V on this region R and 0, 0, minus 3 dot product with 1, 1, and 1, the area. Okay? So simply we're getting a double integral R minus 3 dA here, where the region is given by 6 minus U minus V is greater than or equal to 0. Okay? And I suppose all of you are very smooth about the double integral. So I'm going to just assume this is a U simple region. If I assume it is a U simple region, I need to come up with the du inside. All right? I need to have du inside and dv outside. So I need two numbers for v, which is 0 to 6, and two functions for u, which is 0 to 6 minus b, right? And minus 3. Okay? So that's the double integral we have. And this is exactly the region you talk about here. Right? So if you said this is u, this is v, where v goes from 0 to 6, u goes from 0 to 6 minus v right here. Because this equation is exactly given by 6 minus u minus v is equal to 0. So this is given by 6 minus u minus v is equal to 0. If you want to set up for a u simple region, I'm simply solving u as a function of v, and that's exactly 6 minus v. Okay? Right. This is a u simple region, and then you can do the following. Okay? Any questions? So summarize what we did. If we have a surface integral of a vector field, we have to come up with the parametric equation of the surface to begin from, right? And then I still want to compute the normal direction. But because we're computing the surface integral vector field, we have to worry about the orientation. So this is where you need to worry about orientation. The orientation is usually given by the condition in the problem. For instance, in this problem, the orientation says the normal points upwards, which means if I compute a normal direction, I have to make sure the x component is positive. Okay? If it is positive, then that is exactly the correct sign I want to include in the double integral data. So in the double integral, it's going to be a dot product between the vector field and the correct normal direction. Okay, the correct normal vector right here. And then the following is going to be an evaluation of a double integral. Questions? So I want to give you a couple of more examples of practice. Let's look at a more complicated one. So if I have a vector field which is given by e2 minus z and 4x1, where s is equal to x, y, z, where z is equal to cosine y, y is bounded between minus pi and pi, x is bounded between 0 and 6, and also the normal points upward. Now we want to compute the surface integral of the vector field with respect to this norm. Okay. So what do we do? Still, the keywords is parametric equations, right? So parametric equations. So this parametric equation, even though the function seems complicated, but still we want to try our natural choice, which is setting u to be x and v equals y. But we have to be really careful about your uv, especially if you stick with uv as two letters. Always write them distinguishable. Okay. So my u is x, v is y. So z is actually cosine v here, cosine v. But we can extract the restriction for u and v immediately, right? So r as the restriction is that u goes from 0 to 6, v goes from minus pi to pi. Okay? V goes from minus pi to pi. For this particular problem, I didn't even try to draw the surface. Because for all the surface integral and line integral, you don't have to draw the surface. Okay? Especially if you evaluate here, the only thing you worry about is if I compute the tangent vectors, and when I do the cross product, I need to make sure the z component is positive. That's probably the only geometric factor here. But if you really want to see what the surface looks like, what is this surface? Which type of surface is this guy? So the essential equation is just this kind, right? Z equals cosine y. X is missing, so it's a cylinder in the x direction. This is actually a cylinder in the x direction. Again, in my not so perfect drawing skill, I can try to give you a rough picture of it. But I wanted to stress one more time, being able to draw the graph is going to help you, but it's not essential here, okay? So the way of drawing the cylinder is always in the equation where I don't see x, so I simply on YZ plane see what this curve is. And then in the x direction, I pull this curve to form a surface, right? So that's the way of drawing a cylinder. Y is bounded between minus z and minus pi and pi, so this is minus pi and pi. And z goes from cosine minus pi to cosine pi. So this is the surface on the x direction, okay? So this is the one side of the x direction, and then you're going to pull this curve parallelly in the x direction from 0 to 6, okay? This is a 6, so this is like a so this is the one. Okay? So this is our cylinder right here. So you have a line on the YZ plane, and then you pull this line parallel in the Z direction, you're going to form a surface. Okay? Again, you don't have to be able to draw this to compute whatever is needed here, right? So I want to compute our U prime, which is given by 1, 0, and 0. Be careful, we have U and V as two letters. Always write them in a very clear, different form, so when you compute the derivatives, you don't confuse yourself. Our V prime is going to be equal to 0, 1, minus sine V here, right? Yes? So then I need to compute our U prime plus our V prime, which is going to give me the I component is going to be 0, 0. And the Y component is going to be 0 minus sine V, so it's going to be sine V. And the Z component is exactly 1, which means this is indeed the correct normal vector, right? Because Z component is positive. So the Z component is positive. So we checked. What do I mean by check? I need to check